Hey there. Ready for a deep dive into something truly mind-bending? We're talking superconductivity today, folks. Where electricity flows with zero resistance, like it's gliding on air. It's the kind of thing that sounds like science fiction, but guess what? It's real, and we're about to unpack the science behind it. And to guide us on this journey, we're turning to the words of a true pioneer, John Bardeen, from his Nobel Prize lecture. This guy was one of the masterminds who helped crack the code of superconductivity. So what are we waiting for? Let's dive in. We're talking about materials that seem to defy the laws of physics, letting electricity flow without losing any energy. It's the kind of thing that could revolutionize everything from power grids to electronics, and we're going to figure out how it all works together. Bardeen's lecture takes us on a journey through the history of superconductivity, starting way back in the early 20th century. It was a time when scientists were grappling with some truly perplexing puzzles, like trying to solve a jigsaw puzzle with no picture on the box. They knew something incredible was happening, but the why, the how, it was a tantalizing mystery. Picture this. You've got this thing called the Meissner effect, where a superconductor just casually repels a magnetic field, like it's pushing it away with invisible hands. Then there's the two-fluid model, suggesting there are two different types of electrons in these materials, each with their own agenda. And if that wasn't enough to make your head spin, we've got the London equations, a valiant attempt to wrangle all of this into a mathematical explanation for how these supercurrents even flow in the first place. But here's where things take a turn for the seriously fascinating. Back in 1935, a physicist named Fritz London, the same one from those London equations, had this incredible hunch. He suggested that superconductivity wasn't just some weird electrical quirk. It was a macroscopic quantum phenomenon. Now, usually we think of quantum mechanics as this super weird stuff happening at the tiniest level with particles doing all sorts of crazy things. But London was saying this quantum weirdness was playing out on a scale we could actually see and measure right there in those superconductors. He even went so far as to predict that there must be an energy gap in these materials.
It's like a hurdle that electrons need to overcome to join in on the superconducting fun. He was basically laying the groundwork for understanding how electrons behave in this unique state. But even with these groundbreaking insights, actually piecing together a complete theory of superconductivity, well, that was proving to be a real head-scratcher. Even Bardeen himself, a brilliant mind, admitted to struggling with this puzzle for years. So we're left with this picture of scientists on the edge of a major breakthrough, armed with intriguing clues, but still searching for that missing piece that would bring it all together. So, are we ready to uncover more of this superconductivity mystery? What happens next?
Oh, absolutely. Fasten your seatbelts, because 1950 was a pivotal year in superconductivity research.
Oh, really? What happened in 1950?
1950 was like boom, 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 discoveries left and right. It all started with the isotope effect.
The isotope effect.
Yeah, so imagine you've got two samples of the same element, let's say mercury, but one has slightly heavier atoms than the other because of these things called neutrons.
Okay, got it. Heavier atoms in one.
And here's the kicker. Those heavier mercury isotopes, they actually became superconducting at a lower temperature.
The heavier atoms threw a wrench in the works. That's so strange.
Exactly. It was a huge clue because it meant the mass of the atoms themselves was somehow influencing superconductivity.
So it's not just about the electrons doing their thing. It's about the atoms they're moving around, too.
Right. It's like realizing the dance floor affects how well people can dance.
Huh. I like that analogy.
And this is where those tiny vibrations in the crystal lattice, the phonons, come into play.
Okay, right, the phonons. So how do heavier atoms affect those?
Well, heavier atoms mean slower vibrations. Think of it like a bigger bell. It makes a deeper, slower sound.
Ah, I see. So the heavier atoms were making the whole lattice vibrate at a lower frequency.
Exactly. And that change in vibration, those phonons, directly affected how the electrons were interacting.
Wow, so it's not just about the electrons themselves, it's about how they're interacting with the vibrations of the atoms around them. That's wild.
Precisely. The isotope effect was a huge clue that electron-phonon interactions were playing a key role in superconductivity.
So the isotope effect really shook things up in the world of superconductivity research. What else was going on in 1950?
Well, on top of the isotope effect, you had Ginzburg and Landau coming up with their equations, a really elegant way of describing what happens right when a material transitions into a superconductor.
So like a mathematical snapshot of that magical moment.
Exactly. And if that wasn't enough, Fritz London, the one who predicted the energy gap, he published his book Superfluids that year, full of incredibly insightful predictions about the nature of superconductivity.
Wow, 1950 was a big year for superconductivity. But we still don't know how those electrons are actually pulling off this zero resistance trick, right?
You got it. We have a bunch of pieces, but how they all fit together is still a puzzle. But that's where Bardeen and his colleagues come in.
All right, so what did Bardeen focus on in his lecture?
Well, he really dives deep into these electron-phonon interactions, taking it a step further to explain how those interactions actually lead to superconductivity. And that's where things get super interesting.
Okay, so we've got these electrons and these phonons, these little vibrations, and we know they're both involved in superconductivity somehow. But how do they actually work together? Like, how do they team up to make electricity flow with absolutely zero resistance?
Well, that's the million-dollar question, right? And Bardeen's lecture lays out this really elegant idea, which is that the electrons interact with each other by exchanging these tiny packets of vibrational energy, those phonons we were talking about. And get this exchange, this little back and forth, it can actually create an attractive force between the electrons.
Wait, hold on. So you're saying the electrons are like tossing these little phonon balls back and forth?
Exactly, like they're passing notes or something, and sometimes those notes, those phonons, they bring the electrons closer together.
Okay, I kind of love that electrons sending secret messages through vibrations. But how does attraction, even between electrons, lead to zero resistance?
All right, so here's where things get really wild. This attraction that the phonons help create, well, it can actually cause the electrons to pair up, forming something we call Cooper pairs. And these Cooper pairs, they're the superstars of superconductivity.
Cooper pairs, huh? They sound like a dynamic duo. What makes these Cooper pairs so special?
Well, imagine this. In a normal conductor, the electrons are constantly bumping into stuff. Impurities, vibrations in the lattice, you name it, and all that bumping and scattering, that's what creates electrical resistance.
Okay, I'm following so far.
But Cooper pairs, they're different, see? They're like a perfectly synchronized dance team. They move together in this incredibly coordinated way, gliding through the material without all that bumping and scattering that the single electrons run into.
Wow, so it's like the power of teamwork. By pairing up, the electrons can avoid all the obstacles and just flow smoothly. That's pretty cool.
Yeah.
But how did scientists go from this picture of electrons and phonons doing their thing to actually understanding it all mathematically? Bardeen's lecture mentions these things called Feynman diagrams. What are those all about?
Ah, yes, Feynman diagrams. They're like a secret language that physicists use to describe how particles interact. But don't worry, you don't need to be fluent in Feynman to get the gist of it.
Yeah, that's a relief.
The key takeaway here is that Feynman diagrams give us a visual way to represent and calculate the probability of different interactions happening, like those electron-phonon exchanges we've been talking about.
So it's like a way to map out all the possible ways those electrons can toss those phonon messages around.
Exactly. And the amazing thing is, two brilliant physicists, Migdal and Eliasberg, used this language of Feynman diagrams to make some groundbreaking calculations about superconductivity.
Okay, so tell me more about what Migdal and Eliasberg figured out.
Well, first, Migdal, he came up with this really clever way to use Feynman diagrams to accurately calculate electron-phonon interactions. But here's the thing, he did it for normal metals, not even superconductors.
So he figured out how to listen in on their regular conversations, not just the lovey-dovey Cooper pair stuff.
Yeah, exactly. And then Eliasberg came along and realized, hey, we can actually apply the same framework to superconductors too. He showed that with a few tweaks to account for those Cooper pairs, we can use the same mathematical language to understand how electron-phonon interactions work in the superconducting world.
That's impressive. So we went from this vague idea of electrons and phonons doing their thing to a pretty solid mathematical way to describe their every move, even in the bizarre world of superconductivity.
Precisely. And the story doesn't end there. Bardeen's lecture also talks about these experiments called tunneling experiments, which provide a really cool way to actually see those electron-phonon interactions happening.
Tunneling experiments.
Yeah.
That sounds intriguing. How do those work?
Okay, imagine you have this super thin insulator, a barrier, and you shoot electrons at it. Now, common sense would say those electrons, they can't get through, right? The insulator's in the way.
Right, they just bounce off.
Well, that's where quantum mechanics throws us a curveball. Because in the quantum world, there's a small chance those electrons can actually tunnel right through that barrier, even if they don't have enough energy to go over it.
Whoa, so it's like they're teleporting through the wall? That's mind-blowing.
It is pretty wild. And when you do these tunneling experiments with a superconductor, that's when things get really interesting. By measuring how many electrons make it through at different voltages, you can actually map out the energy landscape of the superconductor.
So it's like using tunneling to peek behind a curtain and see what's going on inside a superconductor at the energy level.
Exactly. It's like we're eavesdropping on those electron-phonon conversations, confirming they're actually happening the way the theory predicted.
So the theory predicted this whole intricate conversation between electrons and phonons, and then the experimentalists came along with their tunneling experiments and showed that, yeah, that's exactly what's going on.
Exactly. And not just in one material either. They saw this confirmation in multiple superconductors, from simple metals like aluminum to more complex ones like lead. It was a huge win for the electron-phonon theory of superconductivity.
So we've gone from those early puzzling observations to a deep understanding of how electron-phonon interactions create this incredible phenomena of superconductivity. It's pretty amazing to think that these tiny particles, dancing and interacting with each other, can have such a profound effect on the way electricity flows. But just like with any great discovery, this is really just the beginning. Who knows what other secrets of superconductivity are waiting to be unlocked? And that brings us to the end of our deep dive into the world of electron-phonon interactions and superconductivity. I hope you enjoyed this journey through the history and the science of this mind-blowing phenomenon as much as I did. And hey, if this deep dive has sparked your curiosity, if you're as fascinated by the possibilities of superconductivity as I am, well then keep exploring, keep asking those big questions. Because who knows, maybe one day you'll be the one to unlock the next big breakthrough.